festivities, and this is a wonderful evening. So, on behalf of Columbia University and the GR21 conference, it is my great pleasure to welcome the Gruber Foundation and the co-founder of the Gruber Foundation, Pat Gruber, here for this wonderful lecture and the celebration of discovery, celebration of science, and celebration of the Gruber Prize. And I would like to also emphasize the presence of my old friends, Rainer Weiss, Kip Thorne, and the brother of Ronald Drever. They are the founding fathers of LIGO, the discoverer of gravitational waves. So, my pleasure, Pat Gruber.
Thank you. Thank you, and welcome to the 17th Annual Gruber Cosmology Prize, honoring a leading cosmologist, astronomer, astrophysicist, or scientific philosopher for theoretical, analytical, or conceptual discoveries leading to fundamental advances in our understanding of the universe. On behalf of all of us at the Foundation, we are pleased to be here at Columbia University to present this prize at the 21st International Conference on General Relativity and Gravitation. Thank you, Professor Marca, for your warm welcome. The Cosmology Prize was established in 2000 as the first Gruber International Prize, and I'd like to acknowledge the founding vision of my late husband, whose leadership in establishing these prizes, as well as acknowledge his passing. Peter died in 2014 after leading a long and productive life. Born in Budapest and being Jewish, he fled Hungary with his family during World War II, later settling in India as a child, where he was educated by Jesuits in the Himalayas. As a young man, he came to the US and eventually went to work on Wall Street. His success as an asset manager allowed us to establish the Foundation and its International Prize Program. To continue this legacy into the future, we reached an agreement in 2011 with Yale University, establishing the Foundation there, where the science and the human rights programs continue. Yale has hired our own Sarah Rea to guide the Foundation, and I will remain a lifetime trustee. The Cosmology Prize is presented annually in conjunction with the International Astronomical Union, whose support and partnership has guided our efforts since the earliest days. It is my pleasure to introduce now Sylvia Torres-Pembert, President of the IAU, who will say a few words about this fruitful collaboration. Dr. Pembert.
Good afternoon. The International Astronomical Union is pleased to have collaborated with the Gruber Foundation on the Cosmology Prize since the prize's inception. The IAU has had an advisory role in the constitution of the Selection Advisory Board, and as part of our collaboration, we are fortunate to receive an annual grant of $50,000 to be awarded to postdoctoral fellows from around the world to be used to pursue education and research at the Center of Excellence in their fields. The fellowship for this year has been awarded to young scientists, but for the previous year has been awarded to young scientists from Algeria, Chile, Poland, Taiwan, India, Mexico, Spain, Italy, Israel, Greece, the Russian Federation, United Kingdom, Colombia, and the United States. The 2016 Gruber Fellows are Maria Nikolayevna Dozdrovskaya from Leiden University and Leticia Del Res from University of Liège. The prestige and reputation of any award is determined by the quality of its awardees. By this criterion, the Gruber Cosmology Prize has done superbly. During the past decade, these recipients alone could write an authoritative history of the universe as any group. Thank you.
Thank you, Dr. Torres-Pembert. We are here to honor the achievements of Rainer Weiss, Kip Thorne, Ronald Drever, and the entire LIGO team. First, let me tell you a little bit about the company they are keeping. The Foundation's prize program, established in 2000, presents 3 annual $500,000 prizes in the fields of cosmology, genetics, and neuroscience. Each prize recognizes achievements and discoveries that produce fundamental shifts in human knowledge and culture. The Genetics Prize will be presented at the annual meeting of the American Society of Human Genetics to Michael Brunstein and David Alice. At the annual meeting of the Society for Neuroscience, the Neuroscience Prize will be presented to Mu-Ming Hu. Returning to cosmology, the 2016 prize recipients were selected by a distinguished Cosmology Prize Advisory Board, whose names you will see on the slide. We deeply appreciate the knowledge, the commitment, and the enthusiasm that these advisors bring to the judging process. Let me now invite the Advisory Board Chair, Robert Kennicott, to present the official citation and introduce the scientific accomplishments of this year's Cosmology Prize recipients. Rob.
Thank you. I'll begin by reading the citation, which is quite a nice reading. The Gruber Foundation proudly presents the 2016 Cosmology Prize to Rainer Weiss, Kip Thorne, Ronald Drever, and the entire LIGO team for pursuing a vision to observe the universe in gravitational waves, leading to a first detection that emanated from the collision of 2 black holes. This remarkable event provided the first glimpse into the strong gravity regime of Einstein's theory of general relativity that governs the dynamics of black holes, giving direct evidence for their existence and demonstrating that their nature is consistent with predictions of general relativity. That's the citation. I could just say a few more words about the context of the prize. It was our intent this year to actually recognize 2 very closely related but distinct contributions. The first was to recognize the seminal contributions of Ray Weiss, Kip Thorne, and Ron Drever over a period of decades, the greater part of their careers, in developing gravitational wave interferometry, and to the benefit, obviously, of the LIGO team, but moreover to the benefit of the entire subject. So it's that sustained intellectual brilliance, scientific leadership, and human perseverance that we are recognizing. Also, of course, we're recognizing the spectacular discovery from last fall that was announced earlier this year that galvanized not only the astrophysical community, but the scientific community as a whole and the general public. We thought for that it was only fitting to recognize the entire LIGO team, not any individuals. Those of us on the advisory board are quite proud of the fact that the Gruber Prize is one of the few that can recognize a team achievement, and there's never been, I think, a more appropriate use of that. So with that, we'd like to proceed with the presentation and ask Pat to return to the stage along with Ray Weiss and Kip Thorne. Ron Drever, as many of you know, is, due to health reasons, is unable to attend the ceremony, but his brother Ian has kindly come to accept on his behalf. And before we get started, since I know there are many members of the LIGO team who are co-recipients here today, I'd like to ask at this point if those individuals could stand and accept the appreciation of the rest of us as well.
Thank you very much for this, and it's a great honor to have received this award. But it's also, I think, I'm a symbol for the people who got up and others who are not here. I hope you see it that way. And I wanted to tell a little story in this 1 minute that I have. But I almost wrecked it for you by doing the following. I was sent to one of the sites to fix a problem on the Thursday before the Monday where we made the detection. And I was told by the people who sent me, it's going to take me a week to fix this problem. And I was very insistent that we fix it, because I thought it might disturb the measurements. But then wiser people said, no, everybody's coming to the sites. We have to run when the time was given to do the run. And thank God they overruled me.
I would like to thank the Gruber Foundation and Patricia Gruber in particular for this wonderful honor. I had the great good fortune to build a collaboration with Ray Weiss and Ron Drever, and as a result, I, as a theorist, wound up working very close to experiment, contributing a little bit to the experiment, and so here I am today. So I need to thank also Ray and Ron and the superb LIGO team who made us look so very good. Thank you.
Mrs. Patricia Gruber, the Gruber Foundation, ladies and gentlemen, my daughter Anne and I thank you for inviting us to attend tonight on behalf of my brother Ronald, known to most of you as Ron. Ron was diagnosed with dementia when he was at the Caltech in 2008. Treatment began then, continues. He now requires to be in a care home and is happily settled in Edinburgh near where I live. He is not fit to travel, but amazingly has picked up greatly over the last few months. Whether because of the knowledge of the incredible success of LIGO or the increased stimulation from the discussions generated, we cannot say. Ronald is aware that he is being presented this award today and is thrilled. A celebration is planned when we return home for family and residents and friends, when we look forward to passing these remarkable elements to him. We recognise this is a collaborative achievement requiring not just the scientists, but also a vast network of support staff behind the scenes, something Ronald was always highly concerned about. Ronald and the family, therefore, send their congratulations to all involved and sincere thanks to the Gruber Foundation for recognising this momentous discovery. Thank you.
Congratulations once again to our recipients. Drs. Thorne and Weiss will now present the Gruber Lecture entitled The LIGO Project, Beginning to Future. Thank you.
See, Kip is being the technician for me. That's good. Kip and I have decided to give a talk together, and let's see how it goes. We're both going to talk about beginnings in our lives about this, but also, in Kip's case, more about some things that have to do with the future, which is very interesting, I think. And let me start by this, as you just heard, this very interesting thing we've discovered. got into the society in a way that I would never have imagined. In other words, you hear, for example, and many of you who live in New York may have seen this, is a thing that is in the New York City subways. When I came down for John Levin's book review, there it was already, and I saw it. And it says, if you should be able to read it, but scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in. And then that was shortly after the discovery. And then very shortly after that, New York ran this little cartoon, and was that you I heard just now? It's one bird talking to the other, or was it two black holes colliding? See? And what, of course, is being referred to is the chirp that we heard. Okay. So I want to take you to the thing which many people do not know as the start of my talk. And that is a historical thing, which is that Einstein in 1916 wrote this paper, which was the beginning of this. And he wrote at the end, and I won't go, he made some mistakes in it, that's not important. But the important thing is he says something really very interesting at the end. And it's translated right here. It's in any case one can think of, A will have a practically vanishing value. What A is the strength of the amount of power radiated by the gravitational waves. And he thought, by the time he got done with it, he's so tiny that it was impossible to measure, it would have no function in physics at all. And here, we can't find the actual papers that, back in the envelope calculations that he did this with. So I did something and made believe I was Einstein, which is not easy. And so I use a formula which is very simple. What that formula has this is sort of the strength of the strain of the gravitational wave, the thing we measure. It's the amount of stretch divided, the additional stretch divided by the separation of particles in space. And what's in it is these are the things that make it. What it is that this is the constant that you learned about in high school, the gravitational constant of Newton, the mass of the system, and then this is the distance you're away from it, and this is the velocity of light squared. And that whole quantity is multiplied by the velocity squared, the velocity that is not spherical in the motion. So for example, the example that's here, two trains colliding with each other, which you could have easily imagined Einstein thought about, gives you a number for this strain with the parameters I'm not going to read to you, you can read for yourself, of only about 10 to the minus 42. Now, we measured something at 10 to the minus 18, 10 to the minus 21 in strain, 10 to the minus 18 in meters. And that is so much bigger than this number that Einstein could easily have said, this is made his conclusion. So then he might have very well gone to look at a binary system of stars, of the kind that he might have heard about at the time. Those two stars that sort of had a period of a day. They might be the center of our galaxy. And well, the H value for that is about 10 to the minus 23. But that's possibly measurable, and maybe people will try to measure that now with LISA. But then he said, if I'm going to look at the system, can I see the effect of the gravitational radiation on the system itself as it changes its shape somehow? And if you do that, you find out it takes 10 to the 13 years for the gravitational waves from these two objects having these parameters to even change and approach each other so a little bit, so you can see it on the telescope. So I can see it, and everybody can see very well why Einstein made that very negative statement in 1916. And it's really a testimonial to the last 100 years of both scientific advance and technical advance that we were able to succeed in the last year. So I want to go a little bit back and give the background, how it came about that we were able to do this. These are some important people. This is Robert Dickey, and he was at Princeton. He was a guy who was at the beginning of the renaissance of going back and doing gravitation as physics, not just as mathematics. And he did something which I can only describe. He did an experiment. I'm having trouble seeing this picture. So it's a picture which has three masses in it, and he was doing the Enclosure experiment all over again, trying to see if all masses fell with the same way. And he did it using the sun. And he did something which is very important to us, which is here are these masses in a triangle. Here I can see it. And it's being measured, they're being measured, and what is being done is they're being held by a system that's called a servo system that keeps them from moving. And that is the way to do the measurement. You don't let it move, and you measure the amount of force you have to apply to make the thing stop. And that's a technique that's used all over LIGO. It's everywhere. And so this is a very important development that came from Bob Dickey. And then the next most important development, that's why I don't want to give you the difference, but is Joe Weber himself. And Joe, at the 1957, with Wheeler together, began to think of how could it be that you could measure the gravitational waves from something astrophysical. And instead of just writing it down and pondering about it, he actually tried to do something about it. And that's what is here. This is Joe, and this is the instrument he used. He used an instrument where he was hoping that the stretching of space and in one dimension and the contraction of space in the other dimension would be something that would, if a pulse of gravitational wave went through this, it would leave this thing ringing. And that he mounted all sorts of sensors on it, and he actually, it was a big xylophone in effect. And he was hoping that a gravitational wave would come along and leave it singing. And it was an idea he worked on for many years. And a lot of other people began to do the experiments he was doing because he did think he saw something. And these are other groups that were doing it. I won't go into all of that, you can see them. The groups are people all over the world, and people are still doing this now with great big spheres instead. But the trouble was, in the epoch of the 60s and the early 70s, nobody else saw what Joe Weber saw. And what happened is that other people who were beginning to think what to do, how to make these kind of systems better and better, were pondering how to do that. And here is one way that people thought about it. And this is the thing that actually led to LIGO. And the idea came really from an experiment. This is, again, from a meeting which was in the Chapel Hill meeting in 1957, where the bar idea came up. But this is actually the man that F.A. Palani came up with the idea that is central to the interferometric idea of doing it using three masses. He actually showed that you rigorously got the same answer by many different ways, by taking two masses, letting them free fly in the universe someplace out in space, and then measuring the time it takes for light to go from one mass to the other, using that as the metric. You then bring a gravitational wave to come between them, and then the time would change. And that was the basic idea. And he then laid out the mathematics for that. And it became real. And it became something independent of the coordinates. That was adopted by me then in designing a system that was very much like it's not exactly what LIGO built, but this was one of the first ideas for this. Other people, by the way, had similar ideas. Gerstenstein in Russia had a similar idea, but he never worked it out. And then Bob Forward at Hughes, who was a student of Weber's, had a similar idea, wrote a paper about it, but again, not in the same concept as here. Here the idea was to use free masses and let the light bounce back and forth many times between free masses, and then also do some modulation of the light, so you could very well get over the noise in the light itself, especially the added noise from the lasers and stuff like that, so you modulate the light. So the principal ideas of this were to hang the masses in some way so they were free, not like a Weber bar, use light to measure the time it takes light to go on the two arms of an interferometer, that was the other piece, and then to modulate the light. Those were the basic ideas. And a lot of people began to do that. Here, for example, at MIT, there was a small prototype built, and then the group that really made it work in the first go was the group in Germany. And this is the group at the Max Planck, and each one of these people really had an idea that one of the ideas was to actually to make a way of fixing the light so it was more pure. Schilling then had the idea of fixing the light also so it had single frequencies, and also the idea that you might somehow bring the light back that is wasted in the interferometer. I'll show you that in a minute. So the recycling is an idea he had, but so did Ronald Drever had that idea. And then Winkler knew how to do the optics, and Maischberger had this outrageous idea of hanging all the components, not just the test masses, but every component that touched the light was hanging. That was something that you normally wouldn't have. And Frau Schnupp had the idea of taking out those modulators, those things that modulate light, and make it so that they make a slight unbalance in the arms of the interferometer to bring a signal so you could measure it. And this group then solved many of the problems that were endemic in this thing. But then also the group in Glasgow, which was the group that was run by Ron. And Harry Ward, who was in the group, figured out a way to align the interferometer, which is still being used. And Brian Mears figured out a way to make the interferometer so you could tune its spectrum, which was very clever, and let's get to that. And then Jim Huff was the first meeting with Ron Drever to try out Fabry-Perot interferometers instead of what was in this design here, where it was delay lines. So they are comparable things, but this was much harder, I felt, to do. And then Ron, of course, orchestrated all of this, and he then actually helped with Mears developing the, what's called signal recycling and also the power recycling. And then he left Scotland to join Caltech, but we'll get to that in a minute. Here then is the interferometer that is sort of what came out of the thinking of all these groups, and that's the one that is at the sites. And I won't go through it because you've heard a lot about it. I just want to point out these refinements. The refinements are that here is the Fabry-Perot cavities. These are the things where the light bounces back and forth many times. It does the same on this side. The gravitational wave is coming down on it. What it's doing is stretching this arm, causing the light to take longer time in this arm, and shrinking that arm for less time in this arm. And that's very simple, straightforward microinterferometer with Fabry-Perot cavities in terms. The new idea is this power recycling mirror right here, which is a laser you stick between, which is a mirror you stick between the laser and the beam splitter of the interferometer. And that was the thing that occurred to both Ron and to Schilling. And then this is the idea that was Ron and Mears' idea to feed back the signal between the detector and feed it back. It's quite subtle what that does. As it does what I told you, it changes the spectral response of the interferometer. So that is the device that actually is the outline of the device that made the detection. Now I want to talk a little about what the process was. And the first thing that happened is that up to now, all this stuff I showed was sort of early 70s. And in 1975, I was asked to run a committee by NASA to look at what you could do to improve the knowledge of cosmology and gravitation using the space program. And that's the program of the outline of the report we wrote. And then here is a little bit about the people. And you'll see that I asked Kip to be on that committee. I didn't know Kip well. And by the way, a thing that's important is Kip, Joe Weber, and I were all simultaneously at Princeton in that epoch in the end of the 60s, beginning of the 60s. So it's sort of interesting that we happen to be concentrated there. Okay. And anyway, I knew about Kip. He had got this wonderful theoretical group at Caltech, and I wanted him to be a person who would be on the committee, but he said it was too busy, and so he was a witness to the committee, and he came to Washington, and here he is. This is you'll see him, but that's what he looked like. And he came to Washington, and we spent one whole night talking. And what was the talk about? The talk was about Caltech already had this very good group in its theory. And Kip was thinking that they also have a very good group in experiment. And Kip and I talked about all the different kinds of experiments that, not only for the space program, but for gravitation in general, and even cosmology measurements that could be made. And I told him about these interferometric techniques. And he got very interested in that. And he'll tell you a little more about that maybe. But a lot of this, the thing that became a textbook for all of us was this book here. And that is like the New York City telephone book, a big fat thing. And it has in it a marvelous chapter on all the ideas for sources at those days, and also ideas for how you make detectors. But what's missing, the interferometric detector. Now, okay. Kip and I, between that time, began to talk about it. And I, in fact, recommended to Kip, and all the pictures that I pictured, all the people in the German group, all the people in the Scotch group, especially Ron, I recommended to Gruber that recommended to Kip that he'd think about, he's to start a group in this business to see if any one of those would be suitable for Caltech. Now, while this is all going on, there is also something very important going on in the National Science Foundation. And this is the person who is really, as far as I'm concerned, singularly responsible for the fact that we kept this project going from middle 70s all the way to, think of it, 2015. And we only had a result in 2015 and 16. Somehow this had to do a thing for that many years and have a government agency have faith that you were not crazy and you continue to support it. A lot of that is the doings of Rich Isaacson, who convinced his boss, Marcel Barton, who was here at Columbia. By the way, Rich was a Columbia student. but he was the guy who was, in fact, a high-energy physicist, Columbia Nuclear high-energy physicist. Rich has a nice hobby, which is that now he's a curator for rugs and textiles in a very elegant and intellectual way. But he wrote a very important paper, which is part of why he wrote a paper that showed that you actually had energy that was leaving a source that was radiating gravitational waves. And one of the first, there was a lot of controversy about that. So Rich was a very important person in this whole effort. And he gave us money to run a study of how you would make, with the prototype, this is a study of how you would make a LIGO, not a prototype. How big does it have to be? How good does the vacuum have to be? A whole set of engineering questions, and how much might it cost, and how long might it take to build? And we did a big study, and central to that study was Peter Salson. And also, in a way, not he didn't start it, but he joined us, was Sam Whitman, who came in and helped us with looking at how Atomic Pro would do this. This study, then, became sort of, we got funds from the NSF for that in 1979, and by 1983 we gave a presentation. But then let me just go on to what was studied. I think I told you what was studied. So here is the next step. We take this study, we gave it to the NSF in 1983. You go in front of a committee, and that committee looks at it. You see the red line, here they are. There are other big projects that were being discussed at that time in the physics branch. But we were on the program to discuss this study, and especially how you make a big laser interferometer. We were talking about a order, somewhere 100 million, between 100 to 80 million, something like that. And that was big money for this field. It was a huge increase in the amount of money into the field, and quite risky. And so what happened, here's a committee that looked at this proposal, looked at these projects, and here, for example, on that committee, one of them was Stanley Desmond. Right there. And he's a theoretical person with a quantum mechanical theories, but who was interested in gravity. And he was on the committee. They wrote a remarkable, and to me, unbelievable report, which you can't read, but I'm going to read to you here. This was out in 1983. And the committee is impressed with the long-range scientific potential of gravitational wave detection. It will not only test our basic understanding of gravitation, but provide an entirely new window on the universe. We have considered the major interferometric laser detection system now being developed by the Caltech and MIT groups. We note that not only is this an outstanding scientific opportunity, but the foundation, which is the National Science Foundation, is the only source of support for ground-based gravitational physics. As with any attempt at qualitative advance, there are risks. Here, the uncertainties involve both the magnitude of the signals to be detected and the large extrapolation of known experimental technique. In other words, going from prototype, it's some numbers of meters long, to something that is now going to be tens or order of tens to ones of kilometers long. And we find, however, the fundamental scientific merits of such an investigation so important as to be worth a substantial investment. That was a huge push for this field from the NSF. Okay, the next step that really was absolutely profound in this whole thing was a discovery by Russell Hulse and Joseph Taylor of the binary pulsar system. Because finally, it's settled when they actually did the analysis. And that is when they say what that is again, it's two neutron stars, much like that little example I had with Einstein, but with real big masses, very close together. And so consequently, the periods are much faster, and the gravitational strengths at the sources of gravitational field strengths at the stars are much larger. And so consequently, they began to see that they could only fit the orbit of those two objects by radio astronomy, by the way, by just looking at the pulses of the pulsar. They could only fit it if they included the recoil effect of gravitational radiation. That was a real accomplishment, and it's really set the whole thing that gravitational radiation was real and palpable on its feet. And this was a fantastic step forward for us, because suddenly we could say to people, there's an assured source. Okay? And now, here's an interesting thing that happened in 1986. In 1986, Dick Garvin, who was also on the here, wrote a letter to Marcel, the man who was the boss of Richard Isaacson. And I won't say that, let's just read you the underlying part. He was somewhat skeptical. He wasn't against it, but he was skeptical whether now was the right time to put 40 million or even 100 million of dollars of NSF money into an effort to build large baseline interferometers. And he suggested that if they continued with this, there'd be a summer study, which is a big study with people who are not in the field to see if this was worthwhile. And then what happened is we got this. This is the output of that study. And what's interesting is that they said all sorts of interesting things here. I'll just say what they are. They said right away, again, don't build 2 sites right off. Don't build one alone. Make it full length, whatever you need to get the sensitivity that you can detect something. Build to run. Don't build it incrementally. And then continue research on improved detectors along with it. And the final statement was get rid of Thorne, Thorne, Weiss, and Drever as people directing the thing. In other words, put them back in the lab and to the desk. That was a very strong and very powerful recommendation. So here are the folks who did it. And Sessler was a high-energy guy who designed machines, but Boyce McDaniel was at Cornell, again in high energy, and here's Kip Thorne again. And so now we come to we finally have a single director. There he is, Bobby Vogt. And what he guides us through, and these are the various peers, on again. And here's Kip. I see I'm having trouble with seeing here's Kip, right there, and that's the chief engineer. And that's Fred Robb, these are all members, that's all I remember of this proposal. And a very interesting thing, this was a magnificent proposal. Really, it took us more than almost half a year to write it up. But it was a gorgeous proposal. It finally made it so that we got started. This thing went to the NASA Science Board. It was a very clever idea that Bobby had. Couple the scientists with the engineers who were responsible for the different parts of the thing. In other words, this pair was responsible for the buildings, this pair was responsible for the vacuum system, the ordinary vacuum system, and this, and I and Larry Jones were responsible for the big long tubes. And that is a very clever thing to do. What happened is, some number of years later, it turned out that Robbie was a very good director, but he hadn't got sufficient number of people to really do it. And so it turns out that we really got a real start. The real start started with Barry. And he brought on 3 more people who are actually exquisitely important to this, namely Gary Sanders and Al Lazzarini and Dennis Coyne, who were recruited to be in the central part of the administration of this project. And then finally the thing really got going. Now, the reason I could stand here was Stan Whitcomb, is that because he was responsible for the detector, the design of the detector, and also he voted with his feet. He went to the Hampshire site and made sure that the detector worked. So that's really quite admirable, the very first detector we made. And the other thing that Barry did something very smart. He, in 1997, invented the LIGO scientific collaboration, which many of you are part of. And that then became a somewhat autonomous organization that was responsible for the science that was going to be done by this project. And it's a very successful collaboration. And it's still holding even after the detection. Okay. And so now, my last slide, this is the people who now follow. And these are now, we have spokespersons of the people who are spokespeople of the LIGO collaboration. Peter Salson was the second spokesperson. I was the first. And then it was David Lightsey who became the spokesperson. And now it's Bobby Gonzalez, who gave a lovely talk this morning, which I missed, unfortunately. And then, and now what happens is that the directors of the project, after Barry, there was Jay Marks. And then it turns out that Dave Lightsey became the fourth director. And I hope he stayed. So now, here's a group of people that they're not the only people, but I will pull them out as the people primarily responsible for managing the advanced detector that made the detection. And there is Dennis Coyne, who, again, he's now a chief engineer on this thing. David Shoemaker, who was the person in charge of making the thing run smoothly. And Peter Fritchell was effectively the system scientist for the advanced detector. And Valera Flolov was the guy in charge of commissioning at Livingston, where Daniel Sig is the guy in charge of commissioning at Hanford. And I think that's it. Thank you.
Can you hear me? Yes. Loud and clear. Can you hear me in back? Yes. Okay, good. So I want to begin. Oh boy. Let's see if we can bring this back up. Okay, good. Okay, I want to begin with some personal history. I went to Princeton as a graduate student in 1962. At Princeton, I did a PhD under John Wheeler. He was a very inspiring thesis advisor. This was before the term black hole had been coined. He was the first person to really use that word in the scientific community. A few years later, he was working on black holes, and this became a central feature of my interest. Along with neutron stars, there was not at that time any observational evidence at all for neutron stars or for black holes. And I recall talking with colleagues who had been astrophysicists decades earlier, before people understood anything about white dwarfs, and asking, did you think white dwarfs would ever be observed? And being told yes. So I had hoped that black holes and neutron stars would be observed. It was an exciting time at Princeton. The other person who had a big impact on me was Bob Dickey. I sat in Bob Dickey's research group and listened to the experimenters. He was the leader of this experimental group that Ray talked about. I listened to them talking about experimental strategies. How do you do experiments? How do you plan experiments? What kind of experiments are worth doing? And I just absorbed everything that I could. Ray Weiss was a postdoc in Bob Dickey's group, and he was a major contributor to the discussions, and I quite admired him in that era. Though we hardly talked at all, I was just a little graduate student and a hanger-on in the Dickey group. But I, as I say, absorbed everything that I possibly could. But the other person who had a big impact on me in that era was Joe Weber. I met Joe at Princeton as a visitor, but then we wound up together in the French Alps at the Les Houches Summer School, and we hiked together in the French Alps. We talked a lot about gravitational waves. Joe had this vision for experiments to do gravitational waves. He was putting together his experimental apparatus that Ray showed. And he had a dream, and I absorbed the dream. I embraced the dream. And so when I went to Caltech on the faculty in 1966, I built a... Yes, that's me. That's not the photograph that Ray showed from the 1970s. You can see how I evolved from the 60s to the 70s. I built a theory group of 5 graduate students and 3 postdocs working on black holes, neutron stars, and gravitational waves. 1972 was a rather momentous year for this field from my point of view. That was the year that Bill Press, a graduate student of mine, and I put together a paper trying to develop a vision, trying to develop a vision for the science that would be done with gravitational wave detectors, and trying to understand what the long-term future might be over the subsequent decades. Down in the frequency band that became the frequency band of LIGO, the sources we talked about were pulsars, which of course by then had been discovered, spinning neutron stars, and supernovae, but we didn't talk at all about pairs of neutron stars going around each other. The binary pulsar had not yet been discovered, and we didn't have enough imagination to think in those terms, nor about black holes going around each other and colliding. So we were very naive in 1972. But, well, there we were. At least we were getting started. That was the same year as Ray Weiss wrote what to me is one of the most powerful papers I've ever read, certainly the most powerful paper in this field. It was published in an internal publication of MIT, not in the open literature, and this was a blueprint basically for LIGO, a blueprint for the initial LIGO detectors. He didn't publish it in the open literature because he didn't believe you should publish such things in the open literature until you've been detecting gravitational waves. And so there it sits in an internal report. But in this paper, he describes the design for an interferometer. He identifies all the major noise sources that this interferometer is likely to have to face. And in fact, all the principal noise sources that the initial LIGO detectors did face. He describes how to deal with each and every one of them. And he estimates what the resulting noise will be after you've dealt with each of them. And he winds up with a conclusion that you should be able to get into the sensitivity range where you have a shot at seeing gravitational waves if you had a big interferometer. This is 1972. It's an absolutely amazing paper. Now, simultaneously, more or less, with Ray writing this paper in 1972, I wrote a chapter on gravitational waves for this book, Gravitation, that Ray pointed to. I had not yet seen his paper. I had not discussed this with Ray. Both of these things are going on, I think, around spring or summer 1972. And what I say is that if you're looking at, you could imagine doing experiments in which you measure the separation between two test masses, monitoring that separation by laser interferometry, but this is of little experimental interest. I was really naive. And I then spent a large fraction of the remainder of my career trying to help Ray and the experimental team pull it off successfully. And so, in fact, as Ray sent me a copy of the 72 paper, I read it and began to understand. And then I had this long conversation that he mentioned, an all-night conversation right until sunup in Washington in 1975. I had long discussions with a colleague and dear friend, Vladimir Bragitsky, in Moscow, Russia. I was shuttling back and forth between Moscow and the US in those days, and became sort of a theorist adjunct to the experimental group in Moscow. And those two, Ray and Vladimir, convinced me that gravitational wave detection had a real shot at success, and I wanted Caltech to be in the game. So I proposed to Caltech that we build a group working in the field. That proposal went through the Caltech faculty and on up to the administration. When it reached the administration, the president of Caltech happened to be Marvin Goldberger, who had been at Princeton when I was a graduate student. So Marvin, or Murph, he telephones up Bob Dickey, and he says, Kip Thorne is proposing to build a research group in looking for gravitational waves. Is this something that's worth doing? Bob gave it a resounding endorsement, and so here we are. As a result, we went out, and after a search, we hired Ronald Drever, bringing him from Scotland, Stan Whitcomb from the University of Chicago, and the two of them then built a 40-meter prototype and got the Caltech experimental program running. Now, let me say a few words about LIGO's gravitational wave sources and how our ideas and understanding of them has evolved over time. Beginning with 1978, a momentous workshop on sources of gravitational waves, the first such workshop that I think ever occurred. It was in Seattle, Washington. It was convened by Larry Smarr, who was at that time beginning to do, well, it was doing numerical simulations of colliding black holes. At the workshop, we discussed sources, and this is from a discussion session at the end of this 2-week-long workshop. And we identified, in the discussion section, after a number of lectures, we identified various sources that one might go after in what became the LIGO frequency band. Supernovae would be at this level. Now this is the H, the dimensionless strain that Ray talked about, the fractional change in the distance between two masses that are hanging from overhead supports. 10 to the minus 21, 10 to the minus 20. At supernovae, here was an upper limit, and there was great debate at that era whether it was going to be up here or down much lower, and so we showed it as the upper limit here. Compact binaries. By now, the binary pulsar had been discovered by Holson-Taylor, and so this was looked at very seriously as a source. And Clark, Van den Heuvel, and Sutancio went in, and they, on the basis of that one observation, there was one such thing in our galaxy that would spiral together and merge in less than the age of the universe. They made estimates of what the strength of the waves would be from such things in other galaxies more distant, out far enough that you would see an event per year. And it came in here somewhere between a bit below 10 to the minus 22 and 10 to the minus 21. And then we talked about core quakes in neutron stars and various other sources. But the bottom line was, looking at all these sources, that we had to get to a regime of dimensionless strains of 10 to the minus 21 in order to have success. And so there were t-shirts made up for the participants in this workshop, 10 to the minus 21 or bust. And so when the LIGO made its first detection last September, where did it come in? 10 to the minus 21, right on the button, right where we said should be what we should be going after in 1978. That is really remarkable. Of course, it's a lot of luck involved, but it is quite striking that the number we targeted in 1978 was the strength of the first gravitational wave source seen. Now, supernovae were a major source for us in that era, up to about that era. But something happened. This illustrates how our understanding of physical laws has changed as new ideas have come along and experiments have verified them. And that affects astrophysics. So in the early 1970s, Stephen Weinberg formulated a theory of what are called neutral currents for the weak interaction. And that was verified experimentally by several teams. The real crowning verification was by a team that was co-led by Barry Barish, who went on later on to become LIGO's director, whom Ray talked about, who carried us from an R&D project into a real LIGO gravitational wave searching team. So with weak neutral currents having been predicted, this had to do with how neutrinos interact with matter, and having been verified, then there was the question of how does that influence supernova explosions. And so here is one of the first papers doing a numerical simulation of supernova explosions, taking that into account. And it says diffusion of neutrinos in supernova core is investigated on the basis of the Weinberg theory of weak interaction. I should say this is a paper by Katsuhiko Sato in Japan. So the influence of this on supernova explosions is investigated through supernova modeling. We obtained the following results. The core of the supernova becomes opaque to neutrinos. They're trapped. They're confined in the core. Under that trapping, the supernova core will bounce by thermal pressure, which means it will go down, sort of ooze down and bounce back rather gently, instead of coming down, crashing down and bouncing back vigorously, bouncing off of the nuclear pressures. And so the whole story of supernova, gravitational waves of supernovae changed. We were a little slow in the gravity wave community to catch on, and this was truly a situation. Already in the cell of 1978, we were talking about possibly this was wrong, and supernovae would be a source. But by the time of LIGO's, the project's birth in 1983, compact binaries had become our primary source, and we understood the supernovae were not a very good source, although we still hope to see supernovae. Just seeing gravitational waves from one supernova will tell us a great deal. By 1989, when we made our construction proposal, we laid out noise curves here. You probably can't see the numbers, but these are strains ranging from 10 to the minus 23 on up to 10 to the minus 16. Frequencies from 1 hertz to 10,000 hertz. We had said we would build initial detectors with noise levels at this point. This is a factor of 10 signal-to-noise ratio for anything to be really believable if we saw it. So you needed to be above the upper curve in the initial detectors. We said we would build advanced detectors roughly at this level as a second generation. By then, there was a much better understanding of the event rate for neutron star binaries. And so we had upper and lower bounds, estimated upper and lower bounds for neutron star binaries, and the best guess in here. And then we said black hole binaries, we really don't know. It could be roughly the same as neutron star binaries. And so when the gravitational waves, and then when we actually made our advanced LIGO proposal in 2003, we were proposing something that was a little better at high frequencies, a little worse at the minimum of the noise curve. And when the gravitational wave actually came in, the first one, here it is, bang on, 10 to the minus 21. So that was basically where we are today compared to what we proposed in 1989. I want to make a few remarks about theorists' contributions to experiment. One of the nicest things about my collaboration with Ray and Rod and the LIGO team has been to be able to work with my theory group very close to experiment and to train theory students to interact with experimenters. I'm going to give you one example of this that is having and is beginning to have a very big impact on LIGO. It has to do with quantum noise. It was actually Vladimir Brzezinski, again, my Russian friend, who told us back in 1968 that the Heisenberg uncertainty principle was likely to become a problem or an issue in gravitational wave detection, and that you were going to have to worry about, you may measure an influence of a gravitational wave, and it requires such an accurate measurement that your measuring device will kick back and disturb. The stuff that's using, let me be more explicit, light in this case, using light to measure the motion of test masses. You measure test mass with very high precision using light, and the light will randomly kick back at the test mass, perturb it, and in the process will perturb it so much that it gets in the way of making a good measurement the second time. That we were not thinking about interferometers in 1968. He was thinking about bar detectors, a different type of Joe Weber's type of detector, but it was a similar kind of thing for Joe's detector. And already in 68, Brzezinski's worrying about it. In 1980, here's where we were with the interferometers. We had two of the principal sources of noise, or what we call photon shock noise and radiation pressure noise. Shock noise is you use light to measure the separation between the mirrors that are hanging from overhead supports in the interferometer, and the light comes out to the photodetector that is measuring the signal due to the gravitational wave, and the light consists of individual photons that arrive randomly at the detector, and that random arrival is a noise. Then there's radiation pressure noise. The light in the interferometer arm is bouncing back and forth between these mirrors, consists of discrete photons, and they randomly kick the mirrors. And if you increase the light power, then this kick becomes stronger, but the shock noise becomes weaker. And so we were able, in that era, to draw noise, what's called radiation pressure noise at low frequencies, 10 hertz, say, shock noise at high frequencies, say 100 hertz or 1,000 hertz, increase the laser power, and the noise curve goes like that, and there was a limit right at the minimum called the standard quantum limit. And so there we were, Brzezinski in 1968 had said it in sort of general terms, and we were having to face this in our planning in 1980 as we were beginning to think about LIGO. But this assumed that shock noise and radiation pressure noise are uncorrelated, that they're due to separate individual phenomena. And in fact, the physical origin of shock noise and radiation pressure noise was worked out by a postdoc of mine named Carlton Cage in 1981. He was immersed in the milieu of interacting with experimenters. But I didn't propose this calculation to him or this idea to him. It was entirely his own idea. And that's what happens when you take a great postdoc or graduate student, a theorist, and work with experimenters. They think about problems, and in this case, he realized that the shock noise and the radiation pressure noise, they don't come from the laser, they come from vacuum fluctuations going backward into the interferometer from the photodetector, which normally collects the signal, going back into the interferometer and entering the interferometer and beating against the laser light. Now let me just say this in these terms. The vacuum in physics is what you have left when you remove absolutely everything else. And so you remove everything, you don't let anything at all go backwards through the wrong port into the interferometer. Just remove everything. And inevitably, what remains when you removed everything are fluctuations that you cannot get rid of. Because quantum physics says there are always these fluctuations. These fluctuations go entering the interferometer inevitably, and they produce those two sources of noise. But but it's one thing, one single thing, the vacuum fluctuations, producing both forms of noise, Carl realized. That means, Carl realized, that shock noise and radiation pressure noise are correlated. A huge epiphany and a huge change in how we understood these instruments. It was actually Bill Unruh who then realized, building on a concept from Carl of using what's called squeezed light, which I'm not going to talk about. Well, no, let me just say it in these terms. Carl said, you want to not let the ordinary vacuum go in. You want to modify the vacuum. You want to squeeze it. And I'm not going to tell you what it means to squeeze the vacuum if you don't know. If you're a physicist and you don't know, go learn. This is really important. If you're not a physicist, don't worry about it. It's just one of those esoteric things. Let me just say it's marvelous. And so Carl said, let's squeeze the vacuum. We'll send that into the interferometer instead of the ordinary vacuum. And with that cleverness, then Bill Unruh said, we can beat the two noise sources against each other and make them cancel each other. And suddenly, there's a whole new ballgame in gravity wave interferometers. And this is going to be done sort of beginning in the near future. It's going to become a very big part of LIGO in the near future. Let me say a few words about numerical simulations of gravitational wave sources. Sterling Colgate and Richard White at Livermore, they did the first simulations on computers of supernovae back in the 1960s, and they began what has become a major research program ever since, and is still a major research program for astrophysics and for LIGO. Rice DeWitt, also at Livermore at the time, initiated an effort on numerical relativity, moving into the problem of simulating the collisions of black holes, and he brought on Larry Smarr as a grad student. Larry brought on Ken Epley as a grad student. In the 1970s, they successfully smashed two black holes together head-on, non-spinning black holes, and saw what happened. A marvelous simulation, a huge breakthrough in the 1970s. Now, the key thing, of course, is that in nature, black holes rarely ever collide head-on. They go around and around each other in binary star systems, spiral together and merge. That's a much harder simulation to do on computers, but it was obvious to me and to others already in the 1980s that we were going to have simulations of this if we would ever be able to extract the information that came from gravitational waves of black hole collisions. You have to be able to do a simulation on a computer of how the black holes spiral around each other and merge, compute the waveforms, then compare those waveforms with what LIGO sees, then through that comparison go back to the computer simulations and see what was going on. And so this became a very important goal already in the 1980s, was to do these simulations. By 1995, I was the chair of an advisory committee for a collaboration that involved basically all of the numerical relativity groups in the world that were attempting to do this. This is called the Grand Challenge Alliance, binary black hole effort. And working together with sort of overseeing what they were doing, I became very concerned because they were quite hung up. And so I made a bet with them. I won't read the bet, but it says that I bet that LIGO will see gravitational waves before you guys are able to simulate the binary black hole mergers for generic binary black holes. This was a bet, basically a challenge to try to light more of a fire under them. Come 2001, I got scared because they were still hung up. And so I started a numerical relativity group at Caltech in collaboration with Cornell called the SXS collaboration, trying to do whatever we could do at Caltech to help things move along on the simulations. And I pulled out of detailed day-to-day involvement with LIGO at that time. And so on this occasion, I want to again say to the LIGO team, thank you so much for making me look good in an era when I didn't help out at all. I was often trying to help during the simulations, but the experimental work from then on, I was not involved in that. It had very little interaction with the LIGO team from there on. Today, that has succeeded. Several numerical relativity groups around the world have the capability to simulate generic binary black hole collisions and calculate the gravitational waveforms produced by them. Here are just some simple examples, some iconic examples of black hole binaries that have been simulated. You have to choose the masses or the mass ratio. The total mass scales out. The mass ratio and the three components of the spins of each of the black holes, and also whether or not the orbit is circular or eccentric, what the eccentricity is. So there are a lot of parameters, and so it requires many, many simulations in order to cover the whole parameter space adequately. I conceded the bet. They were able to do the simulations several years before LIGO actually made the detection. And also crucial input for LIGO's detections was post-Newtonian calculations of inspiral waveforms that were begun by Einstein, Infeld, and Hoffman in 1938. Dambour, Blanchet, and many others, many people who are here in this room today, contributed to this. A key piece was also something called the effective one body, which was a technique for combining the post-Newtonian calculations with the numerical simulations. And this had to go into building the templates that are used to extract information from the sources and to do the searches for the gravitational waves. All of this came together, experiment simulations and post-Newtonian simulations, on September 14, 2015, with the detection of GW 150914. People who are at this conference, and most everybody else I expect, has seen the data, the marvelous data, the interpretation of the data, two black holes colliding 1.3 billion years ago, 1.3 billion light years from Earth. The credit for this belongs to the LIGO team and the LIGO vertical collaboration. And I would like to give them a hand once more. It's just fantastic. Laboratory group, the group at the Livingston Observatory, the group at the LIGO Hanford Observatory, and that's just a beginning. There are many, many others that are at other institutions. Let me say a few words about the future and then end. Now, there are a number of other sources that advanced LIGO will detect. We expect gravitational waves from spinning neutron stars, that is pulsars, black holes tearing neutron stars apart, neutron stars in a binary system merging, the cores of supernovae, we hope, and we also hope to see gravitational waves from cosmic streams. And above all, big surprises. Every time the humans have opened a new window onto the universe, nearly every time there have been big surprises. And this is not likely to be an exception, because gravitational waves are so radically different from the electromagnetic waves that are our primary source of prior information. Today, advanced LIGO is a factor 3 away from its design sensitivity. This is a noise curve here. Frequency 10 hertz to 1,000 hertz. Strange going from 10 to the minus 25 way down here up to 10 to the minus 22 up there. There are ideas under development for improvements of it beyond advanced LIGO in the 4-kilometer vacuum tubes that we now have. There are ideas under development for 40-kilometer interferometers. There are huge improvements here, a factor of 20 there, another factor of 20 or 30 here, that appear to be possible over the coming, let's say, 2 decades or 1.5 decades. I don't know how long it's going to be, but these ideas are just under development. But there really are the possibilities of some huge, huge improvements in the coming, say, 15, 20 years. And this is just one of the gravitational wave windows that will be opened onto the universe in the next 20 years. This looks at gravitational waves in the millisecond periods. LISA, and after that, something called the Big Bang Observer will look at gravitational waves in periods of minutes to hours. Something called pulsar timing arrays, periods of years to decades. And something called the cosmic microwave background polarization, gravitational waves from inflation in the beginning of the universe with periods periods of billions of years to hundreds of millions of years. By the second half of the 21st century, I'm now going to speculate. I think it is likely that the successors of our generation in the second half of the 21st century will be exploring, as one of the primary things they're going after, an exploration of the first 1 second of the life of our universe. And among the speculated sources in that first 1 second are primordial gravitational waves, whatever came off the Big Bang convolved with inflation at the beginning of the universe. Waves from first-order phase transitions associated with changes in the fundamental forces, for example, the electroweak phase transition. Waves from cosmic strings, domain walls, defects of that sort. Waves possibly from mesoscopic oscillations of our universe as a brane in a higher dimensional universe. These are all wild speculations, but these are the kinds of things that I would expect that the future generations will be studying in the second half of this century. And gravitational waves will continue to be a major tool for astronomy into the next century and perhaps well beyond that. Thank you.